Yeah, so I'm Chris Malone. I'm going to tell you, I guess I should stand by this. I'm going to tell you a little bit about some of the work I was doing at UC Santa Cruz as a postdoc. I'm now at Los Alamos and hope to continue some of this work on Blue Waters, but they also have me looking at things like explosives. So, but there's a lot of overlap. So, type 1a supernova. I guess there are more astronomers here than I expected, so this may be a little bit too high level for some of you, but hopefully not for the majority of you. So I should tell you, what is a type 1a supernova? So astronomers are classifiers. We look at things that we see in the sky, and then we classify them into groups. And so the 1 means that there's very little hydrogen that we see in the spectra of these events. And the A means there's strong silicon. So it doesn't really mean much to you, but it means a lot to differentiating different types of supernovae. So if you were in some of the astronomy talks yesterday, they were talking about core collapse supernovae, which are a completely different beast from the things that I'm going to talk about today. And so what we think type 1a supernovae are basically thermonuclear explosions. So I said there was kind of an overlap to the high explosives I was working on, so this is the overlap. Of basically carbon, oxygen, white dwarf stars, which are, in these particular cases, they're objects that are about 35 to 40% more massive than our sun, but they're compressed into something the size of the Earth. And so they have central densities on the order of 2 billion grams per cubic centimeter, so they're quite dense. And observationally, you can't quite see so well, but this is basically what it looks like. So this is a supernova that went off in 1994, and what you see there in the blue kind of extended region is a galaxy, the host galaxy of that supernova. And the very bright spot down on the bottom left is the actual supernova. So these things are exceedingly bright. They can outshine their host galaxy for months on end. So it's an enormous amount of energy that's released. And so astronomers look at these things called light curves, which is basically the brightness or the luminosity of the event as a function of time. And so this is for one supernova that went off in 2011. And each of those curves are in different parts of the spectrum. So the bottommost curve is looking at the bluer parts of the spectrum, whereas the top curve is looking at the redder parts of the spectrum. But there's a typical characteristic profile for these types of events. So you'll see that there's sort of 2 time scales that these things fall off. So it jumps up and peaks on a very short time scale and then falls off at a very quick time scale and then has a slower decline. And so what this is really indicative of is the nuclear physics that's going on in these events. And in particular, that very sharp initial drop-off is the radioactive decay of nickel-56, which is produced in these events. And so that nickel decays to cobalt on a half-life timescale of about a week, and then that cobalt decays to iron on a timescale of a couple of months. So you get these various features in events. And so by looking at the different parts of the spectrum and comparing the red versus the blue, you get something called color, the astronomers called color, that tells you a little bit about the different processes that are going on and the different elements that were produced in the event. And so why should you care about this? I mean, it's so far away, it doesn't really affect you. Well, it does. And in general, stars, they burn things like hydrogen, helium to all of the heavier elements. And so all those heavy elements get tied up in those stars. And there were talks yesterday about the first stars and the first galaxies and things like that. Well, the supernova that explode, and all supernovae, release that heavier element material into the surrounding environment, and you can produce more metal-rich, what we call metals. That's anything, as Brian said, anything heavier than helium. And so you get that stuff out into the interstellar gas, and you can make new stars with that. And so Carl Sagan famously said, "We are all star stuff." So that's why you should care, because the iron in your blood is made in these types of events and things like that. So why it matters in particular, again, supernovae process these heavier elements, and in particular, type 1a supernovae produce something like about half the mass of the sun in nickel and or iron group elements, so things like iron, nickel, cobalt, things like that. And so they also produce, to a lesser extent, things like silicon that are in our lovely computers that we use, every day, that you've got in your pocket as well, but sulfur and the calcium in your bones and things like that. So these are important in a very widespread and a broad range of things. But there's also importance in the cosmology. And so there's this relationship, it's an empirical relationship. So again, these curves over here are what we call light curves, brightness as a function of time. And so there's this empirical relationship for these light curves that the broader these events are, the brighter they tend to be. And so you can use this if you have some sort of, if you measure some light curve and you notice how broad it is, you know something about how intrinsically bright it is if you can calibrate its distance through other means. So we use these things that are called standardized or standardizable candles that allow us to measure distances to these very, very far away supernovae that we see. And in 2011, this was, the Nobel Prize in Physics was for using these types of supernovae to explain that the universe not only is expanding, but it's accelerating in its expansion. Well, with that said, we can use these things and do a lot of interesting stuff, but we don't really know what's going on in these things. I said, yes, they're thermonuclear explosions of white dwarfs, but there are several different proposed mechanisms for how that can happen. And they each have different, slightly different observational signatures. And so I'm at Los Alamos now, and I gave this talk, or I presented this slide at Los Alamos. You can notice because I mentioned the explosion energy in terms of TNT. It's about 1 trillion Earth masses of TNT. So this is basically one of the models for a type 1a supernova, and it's called the single degenerate model. I'm not going to go into great detail, but this is sort of the whole lifetime of it. You essentially have this white dwarf, this really compact object, in a binary system with a companion that is dumping material onto that companion. And so the companion is accreting this material, it's becoming further compressed, and near the center of the star, eventually you get conditions that are hot enough and dense enough that you can actually fuse the carbon together, and you start burning thermonuclear reactions. It sounds very violent, but it's actually sort of a calming phase in the sense that this energy release, much like a pot on a kettle, drives convection in the interior of the star. So you've got this very simmering convective thing in the center, and it's continually heating up slowly over a few hundred years. Eventually you get a condition where that heating is so rapid that it can't cool from this convective phase or through neutrinos carrying away some of the energy, and you trigger a thermonuclear runaway. And that occurs somewhere near the center, and then that runaway propagates through the star. So I'm telling you this is what happens, but it's very uncertain. This is what happens in this particular model. And so one of the things that we did with Blue Waters was to look at the transition phase between when you have this slow simmering and when you first ignite this, what we call a flame, this thermonuclear runaway in the center of the star. And so some of the key challenges here are linking together these different phases. I didn't go into them in great detail, but each of those phases, the time scale was not to scale. The first part was billions of years of stellar evolution, then millions of years of accreting this material from its companion, then hundreds of years of this convective phase, and then about a second to propagate this thermonuclear runaway through the star. And then there are several thousand years later that you might be able to actually see this event if it were close enough. But linking together all these different phases involves different physics, different codes, and often different algorithms for handling these things. For instance, one of the things that we've done is look at that slow convective phase, and because it's slow, it's technically subsonic. And so if you're doing hydrodynamic simulations, there's something that limits your time step size called the Courant limit, which basically for very slow flows means you spend most of your time worrying about sound waves that maybe aren't so necessarily important. So we came up with algorithms to sort of filter those out, but still keep some of the compressibility effects. And so, yeah, that's basically what I just said. So the simmering is very subsonic. The Mach number is around 0.05. But the flame propagation, the thermonuclear runaway itself can be, it's still subsonic, but it's faster. And so we need a transition between these two. And there's also a mention of scales. We've heard a lot about dynamic ranges of scales. Well, the runaway ignition from our simulations of this simmering phase occurs in a region smaller than about 2 kilometers. And that's actually a single zone in our previous calculations. But the actual thickness of the flame front, the actual burning region itself, is much smaller than a millimeter. But the star is several, a couple thousand kilometers. So to keep that complete dynamic range is, even with a Blue Waters class machine, is almost impossible. So we have to make approximations, and we do the best we can, but put as much resolution as we can. And so this comes to why Blue Waters. Well, simulating the full star, like I said, is about 1,000 kilometers, while resolving that initial region means you need lots of CPUs, even with adaptive mesh refinement. So just to give you an example, that what I have here on the left is the single Maestro is our code for this low Mach number simmering. So that single zone was the one that ran away in our simmering convection. And we turned that into a, like physicists, we try and make something spherically symmetric at first, but we put little perturbations on it. And we put it into what we call an ignition spot. So Castro is our code that handles the compressible flow. And so we really we turned that one cube into a small sphere that we resolved the hell out of. And we initially had 5 levels of AMR and gave us an effective resolution of something like 37,000 cubed, or 135 meters per zone, which in this type of simulation is quite unprecedented. Usual simulations in the literature have something like 1 kilometer or 2 kilometers or 10 kilometers per zone. So we're about a factor of 8 per direction better. And so our codes, they scale pretty well up to a couple 100,000 cores. But the way that we did this was we split it up into 4,096 MPI tasks using 16 open MP threads per task on Blue Waters, something like 65,000 core modules. And so, whoa, that was a little weird. So when I was doing, so I was the one that was doing these simulations. It was just me, and I was outputting these large files, what to me were large. So a single restart file or checkpoint file was 200 gigabytes, and a visualization file was on the order of 100 to 200 gigabytes. And then when I came here and I was listening to talks the past few days, this is like pales in comparison to what everyone else is doing. But at the time, when it was just me trying to analyze that data, it felt like a lot. I had several tens of terabytes of data spread over both Blue Waters, and we ran some at Titan at Oak Ridge. And so I guess depending on whether it's fortunate or unfortunate, depending on your metric, but most of our stuff that we did in these simulations was done on the early science system. So the full system wasn't online, so the I/O wasn't completely up to par with the full system. But by far, it was already superb compared to other machines that we had used. And so handling that data, again, just being myself, having access to Globus Online and things like that, just made it such a more pleasant venture than dealing with other machines. So that's one of the reasons why Blue Waters really helped. So some of the things that we've done. So I mentioned that we had done simulations of this convection and the simmering that's going on. And so on the left, you can barely see. It's basically a slice through the simulation of that convection. So the red is stuff, I believe, going outward, and blue stuff's going inward. And it's just showing you the velocity and how turbulent the convective flow field is. Prior to our simulations here, what people had done in the literature was they had either done some very crude approximation of the simmering phase, or they completely neglected it when they did the flame propagation phase, in the sense that they started with a white dwarf star and they just triggered a hot spot in the center, and there was no convective flow field. And so one of the things that we wanted to ask was, well, in reality, there should be this convective flow field, and at least initially, the speeds of this flow field and this turbulence are going to be quite strong compared to the speed of the flame. And so we wanted to know, does this actually have an effect on the propagation of the flame as it goes out? And okay, I didn't even touch it that time. Someone have a remote somewhere? Our simulations of this convection showed that there was sort of a distribution of where the ignition should occur, but the most typical ignition was about 40 kilometers off the center from the star. And what I'm showing on the right is basically the amount of mass. So the colored curves are the amount of mass of the iron that's produced. And again, the iron gives you a proxy for how much nickel is produced and how bright the supernova will be. The end result is that, including this turbulence, we went to all this effort to make sure we could resolve all this stuff, and including the turbulence for a typical ignition, it basically doesn't have much of an effect on the propagation of the flame as it propagates out through the star. It's less than 10%, which is probably within the observable uncertainties. However, if you were to artificially move that ignition point closer to the center of the star, it does have an effect. So what I'm showing here are 3 different times. So each column is at a different time in the evolution. The top row is without this background convective flow field, the turbulence. And the bottom row is with the convective flow field. So the blue color is basically the velocity field, and the red, which you maybe can see, is sort of the outline of the flame front. And so if you think about it, when you move closer to the center, and here this is 10 kilometers off center, the gravitational acceleration is smaller. And so these bubbles, which are the surface of the flame, are buoyant. And so if the gravity is lower, they don't float away as quickly as they would otherwise. And so they stick around longer, and the turbulence has more time to interact with the flame, and it can distort it. And in fact, you can see at the very later times, it's completely stretched off center because of this localized turbulence field. And so what this indicates is that even if you ignited a perfect sphere at the very center of the star, in the presence of this turbulence in this background, you would get something that's highly asymmetric. And so this is something that's, that hasn't been explicitly stated in the literature, but it's kind of, when you think about it in more detail, it's kind of intuitive that you would expect something like that. And so another thing that we looked at was sort of the evolution of this flame front. So what I'm showing down here in the bottom left is that initial perturbed sphere. And as it burns, initially it burns out laminarly, and so it's very smooth, and it spreads out. But then it starts to, even if there isn't any background turbulence, it starts to generate its own turbulence sort of in a wake, and that interacts with the bubble as it evolves. And so some of these they're pretty illustrations, but they're also quite informative. And I think we had help with Rob and Dave on making some of these visualizations. But there are interesting phases that this bubble actually goes through. And maybe it's known to the people that do terrestrial fluid mechanics, but there's a difference here in that the surface of our bubbles are thermonuclear burning regions, so it's a slight difference. But what's being shown in the other volume renderings is the magnitude of vorticity, which is a proxy for the amount of turbulence. And so there is this evolution in where the strong features of the turbulence are, and essentially it starts out initially on the surface of the bubble, but then as time goes on and things get more and more turbulent, it starts to penetrate into the interior of the bubble, and eventually you get this fully developed turbulent feature. And we looked at this, and you can also characterize this in something we looked at was basically the solid angle of the bubble. So if you're sitting at the center of the star and you're looking out at the bubble, it goes through these different phases. I won't go into details here, but so these are very high resolution simulations compared to some of the other stuff in the literature. And when we do lower resolution simulations, we reproduce some of these features, but not quite all of them. So some of the implications, I already said that if you believe our model, these explosions are asymmetric. That's how they would occur in nature. I didn't talk about it in great detail, but the total amount of this nickel that we produce, the stuff that makes the brightness of the supernova, is quite small in our simulations compared to the other things in the literature, in part because we use a realistically, or what we think is realistic, size for an initial ignition kernel being quite smaller than what other people use. And so therefore, if we have less nickel, then these supernovae tend to be quite faint. And so the main thing is that if you believe our results were to apply to this model, you need something else to try and get a typical supernova, basically. And I didn't talk about the detonation stuff, but that's And you're standing up, so I should stop.